Good morning, everybody, again, and welcome. Today is February 23rd, and we are still finishing chapter 2. And then also, hopefully we can start chapter 3. Before I do that, there is something that is very important. Namely, we have a quiz that I hope that you guys will have a time to prepare for it. It's, let me check on it. I think it's on Canvas already. It's supposed to cover the chapter, what is it, chapter 1 and 2, okay? So hopefully you guys will not have any difficulty with it. And if you run into some difficulties, please let me know, okay? So that's the idea behind it. And we will see how it goes. I think it opens already. Let me check on it because I posted it last week. It's it should be available by this Thursday, by 8 o'clock in the evening, and you basically have 1 week to finish it, okay? So that is something that I probably will make some adjustment before Thursday, so you may already notice that down the road, but at this point, it's scheduled for Thursday at 8 p.m., okay? I hope that some of you, at least I know that one of you guys attended the live basically broadcast and the discussion before the lander on Thursday. If you did not, I hope that you're following the news and see what was done. And there was actually a movie of the landing itself, basically how the Mars lander happened and things like that. And don't forget that you have already a prompt for that. So you're supposed to, if you cannot watch it live, to go and basically watch the session after that and see what happened and things like this, okay? What was I talking about? The other thing also is the, man, I lost the train of my thoughts. Anyway, so we'll get into whatever is needed later on, okay? So today is the finishing, first of all, chapter 2, because I believe we didn't finish it last time because of the fact that we had that event going. So let me share with you the screen, and it's this one. So again, we were just still talking about the laws of Newton. And we basically stated the fact that the first law is merely a reflection of Mr. Galileo's work, in a sense that an object at rest will stay at rest. An object in motion will stay in motion in the same line. It's very critical to keep that in mind, that what we mean by change in motion are two things, or one or of two things. It could be both of them. Where is my writing pen? Okay, it could be both of them, or at least the magnitude of the speed, basically, change the velocity itself, going from 50 miles down to 40 miles, for example. In this case, you change the velocity, or going from 40 to 50. So one case you go less, and one case you go more. So change the magnitude and also the direction. In a sense, you could have your cruise control set at 50 miles per hour, but you're going on a curve. In this direction, in this case, the direction is changing, but the magnitude is not, because of the fact that you have your cruise control, okay? So in this situation, if both of them do not happen, both the magnitude does not change and the direction does not change, we're dealing with the first law of mechanics. Now, the second case is, now if there is a change in motion, namely the magnitude changes, going from 40 to 50, for example, or the direction changes, or both. You could do both. You could go on a curve in the same time, decelerating or accelerating. In this case, we saw that is governed by the second law of Newton that basically states that this change in motion, not the motion itself, the change in motion, whether in magnitude or direction or both, is proportional to the force that caused that. So there is a cause and effect relationship in here. There is causality in here. One thing has to happen first, and the second thing happens later, okay? What gauges this relationship is the inertia. An object with more mass in it will have more inertia, more resistance to this change. That's what inertia is. So it doesn't like, an object by itself does not like its motion to change by virtue of its inertia. The more it has of inertia, the less change in motion it's going to experience for the same amount of force. Okay? So if you would want to have the same effect, namely a greater change in motion, in this case, you better come up with a higher force. So those are the two laws of Newton. And both of them, if you notice, deal only with a single object. Namely, the first one, an object, and there are no net forces. So that is law number one. Second case is an object with net forces. So both of these laws, this is law number two, by the way, both of these laws deal with a single object. The third law, though, deals with the case when we have actually more than a single object, namely two or more objects. So the statement in this case is, if two objects interact, that's a condition. If they don't interact, we resolve each and every one of them either to the first law or the second law. Now, if they do interact, they do so in such a way, if one of them exerts a force on the second exerts a force that is equal in magnitude, but opposite in direction. Case in point in here, this girl is pushing on the wall, exerting a force on the wall, okay? The wall is exerting a force back on her, and this is an interaction. I have two objects in here. Actually, I have the hand and the wall. So that's clearly an interaction in there. So that is the case of the third law, okay? Though again, we call the force is the case of a push and pull because that's intuitively how it looks like, okay? I'm glad that some of you already responded to those comments with those nice pictures and even some videos. They are very nice, okay? So again, I think the assignment is still not over yet, so we're still waiting for it. So hopefully you guys will, once you finish it, we'll probably we'll go through it, at least some of those nice things, and also demonstrate the law of inertia, okay? So again, the law of action, this is the third law of Newton in its full glory, okay? Whenever one object exerts a force on a second object, the second object exerts a force on an equal and opposite force on the first one. So which one is the action and which one is the reaction? They are both, they are interchangeable, okay? So in the first case in here, which one acted, Ravi? You cannot really say that the girl is the one that caused the action because that happened in the same time. The minute the girl pushed on the wall pushed back. So really, if I'm sitting in here right in this point where the interaction is happening, I couldn't tell which one pushed and which one pushed back, okay? Because this is really a matter of just perspective, that's all, okay? So action and reaction, they're relative in this case. It happens at the same time. So whatever you like to call action is action, and the other one, the opposite to it, is reaction, okay? So, so again, one force is called the action force, the other one is called the reaction force, are co-pairs of a single interaction. They describe the same thing. Both of them, they're actually talking about the same thing that happened in that point, okay? They're not two different events. And then neither force exists without the other. They exist in pairs. If the girl, for example, decides to pull their hand out of the wall, at that point, the wall also decides to stop pushing back. So in the same time, they happen instantaneously. So they cannot, it's not like the wall keeps on pushing back because there is no reaction in this case in there, okay? Are equal in strength and opposite in direction, always act on different objects, okay? The first case in here, you have the hand of a girl and the wall. Those are the two different objects. So there is an interaction with two objects. So these are the characteristics basically of this action-reaction forces, okay? So again, now we have a full tally of everything. If I go back into how many objects the third law deals with, at least two objects. Two objects or more, okay? You ask, how about if I have three objects? Well, how am I going to handle that? Well, in this case, I pair them. So I take object number 1 and object number 2. So the interaction between them, object number 3, for example, see the interaction between it and object number 2 and this interaction. And if I am really interested in this object by itself, I could isolate it, remove the other two objects, and now just find the effects of the other two objects on it. And that's the end of it, okay? So this is a prescription on how to deal with real problems when we're dealing with when we're trying to actually solve problems in physics. In physics, we do something called the FBD. F stands for the free body diagram. It's really illustration of what I was talking about there. That's it. You isolate an object. And you use the third law. For example, if that object was interacting with another object and you isolate it, and now you have the object by itself. We're going to talk about this one in this chapter. So we're not going to call it the FBD because it requires a little bit. I mean, if we're really going to use that, it will require geometry, it requires vectors and things like that. But this is in a nutshell the idea behind it, and we're going to talk about it in here, what we mean by a system. And that's exactly the idea behind it. A system, you're isolated by itself, okay? So again, in here, a soccer player kicks a ball with a 1500 Newton of force. The ball exerts a reaction force against the player foot with how much it has to be exactly? Is it more or less than 1500? I can't see the chat right now since I am sharing my screen. I hate this feature of Zoom. They should really fix that.
Would it be 1500 Newton?
It has to be exactly 1500. It cannot be more, it cannot be less. That is by virtue of the third law. That's why it has to be this thing. The reason why is because I have an interaction right now between actually the foot of the player, not the entire player, okay? Just his foot or her foot and the ball. So we have two objects in here, the foot. I'm trying to draw foot in here, okay? And we have a soccer ball, okay? So this interaction kicks with 1500 Newton. The ball kicks back with the same amount of force, okay? Sometimes it hurts a lot when that happens, okay? Especially if you hit it on the wrong side. Again, in here, what causes cars to move? So what's going on with the car when it moves? What pushes the car forward? I'm going to try to make this as a tire of a car. Can I do it? Let me change cameras. Come on, what is cameras? Oh, change this, but this. Okay, let me remove the background. Okay, so what I have in here, this is my demos thing. So if the tire wants to move in this case, okay, wants to move in here, as you can clearly see. So what causes it to actually move forward? So I'm spinning it and yet it's going forward. So what causes it to go forward? Is it me?
Well, yeah. Maybe you're pushing it like that, yeah.
Okay, I'm spinning it, that's all. As a matter of fact, I'm going to spin it right now, and it's not going anywhere. So is it the spin motion that is causing the motion, or is it something else? Let me tell you guys, you do this experiment, okay? On a car, let me change cameras again. Oh, I'm still there. Come on. Okay, so basically on a car, what you can do actually, you can spin the tires. That's all the motor does for you. It spins the tires, okay? As the tire spins, it's going to push, or at least part of the tire, this part of it is going to push on the floor, on the street, okay? Once it pushes on it this way, in order for it to spin, the street pushes it forward. That's what causes the motion. It's the friction. It's the interaction between the car and the street. If you don't believe me, wait until it's, I know it doesn't happen in here in California, but if it's a freezing rain, you know, when it's completely icy conditions, you can spin as much as you want and you can turn your engine to the highest RPM you wish, and the car is not going to move. Why? Because you lost friction. As a matter of fact, in the mechanics engine, what they do in order to balance tires, they lift the car, at least in the old days. Now I think they remove the tire altogether, but they lift the car and they turn the engine, and the tire is spinning and the car is not going anywhere because it lost contact with the road. Okay, so what causes the motion, what causes a car to move forward is actually the friction. And that is a reaction from the ground because the car is pushing on the floor is pushing back. As a matter of fact, if you want to, you can stand right now and think of how it happens when you yourself move. If there is no friction between your feet and the floor, you're not going to be able to move. So it's actually the third law in this case. It's glory, because you push on the ground, you push on the floor pushes you forward. That's why there is motion. And on an icy day, you try to do the same thing, you probably will fall, okay? Because you change your center of gravity. When you do so, your feet are not moving except your body moves forward, bang, and you fall. Okay? So that's what happened in there. So the same thing within this case in here between the rocket and the what causes it to move. It's the exhaust from its engine coming out. It's pushing on that gas that is coming out from the engines. The gas is pushing the rocket forward. So again, it's the third law in this case at work. Okay, and the case, for example, I have a mass and spring system in here. The guy is pushing on the spring is pushing back. If the spring is not pulling back, in this case, the person should fall. Okay, so that is really what holding that person on the ground. And the fact that we are, I mean, if a person jumps up and down, yes, the earth is pulling you, but guess what? You're also pulling on the earth too, with the same force. So that is actually an action-reaction principle. So if you ever doubted that everybody is against you, the planet, the mountains, President Biden, President Trump, whoever you want to name, just try this experiment. Just jump up and down, and you will see everybody is trying to drag you down with that force, including the earth and all of the other things on it. And you're trying your best to pull them toward you, and you're actually succeeding. So that is the third law in action too, okay? So again, all of this are two objects interacting. The last example I mentioned is the fact that you and the rest of the planet basically interacting via the force of gravity. This is exactly the same thing as this experiment in here conducted actually a long time ago by Mr. Galileo himself when he demonstrated the value of G in there, okay? So when you, again, I just was talking about this one. So when you step on the curve, I'm sorry, the reaction to this force, basically in this case, the earth is pulling you down, you're actually pulling the earth with the same force. So if, for example, your mass, let's say, for example, it's 70 kilograms or 60 kilograms, 60 times 10 is 600 newtons. The earth is pulling you with 600 newtons, but you're also pulling on the earth with the same amount of force, which is 600 newtons. Again, that's the third law of Newton, okay? Okay, since we talked about several examples in here already, I want you to, in the discussion, at least for this item, to mention a few more examples on an action-reaction principle. Anything that you can think of in terms of what you can come up with for an action and reaction, okay? You can think of anything as long as there are two objects and these two objects are interacting from your daily experience, okay? Did you already get the assignment in here for item number 1?
And that's for discussion 2 or discussion 3?
It's going to be a continuation. Oh, no. It's going to be a new tab that is going to be open, okay? It's
Okay.
part 2 of the same chapter, okay? So
Okay.
that's a big question in here. Now let me go into the modules in here. And no, you're right. You're absolutely right. So let me create the assignment. That's a very good question because sometimes it should be on your modules now, okay? Because this is a new recording anyway that we need to publish for at least the few people who are not here. Do you guys understand the assignment? Just list from your daily experience. You need a key element in here, two interacting objects. If the two objects are not interacting, then you have a problem. So you have to identify the interaction and the two objects. And you say, here is an example of the third law. The two objects are, and the interaction is, and the action is, and the reaction is, okay? It doesn't have to be too complicated and you don't need to think too much about it, just from whatever you can think of, okay? So anything that drops, anything that you can push on it, you can pull on it, springs, whatever you can think of, okay? This is not supposed to be a big assignment in terms of, but just think of the third law in your daily experience in there, okay? And if you have difficulty, just Google something, okay? Okay, again, action, reaction on different masses. If the mass of the object is applied to the two objects of different masses, again, in this case, that resolves back to the second law of Newton. Mass plays a role in a sense that the forces are the same, identical. But if the two objects now have different masses, well, in this situation, the bigger object will suffer the least change in motion versus the smaller object. And what I mean by bigger and smaller in terms of inertia. More inertia, less change in motion or less acceleration. Less inertia, more acceleration. So, and where do we get this from? It's actually from the second law of Newton, because the inertia now plays a role in making the change in motion inversely proportional with the mass. But because the third law, all it says is that two forces are the same, because the forces are the same, now the change in motion is indirectly proportional to the inertia. Here is an example of that. You have a cannon and a cannonball, okay? The cannon usually is made out of very heavy materials, okay? And very bulky and big, whereas the cannonball is lighter in mass, relatively speaking. I mean, it's heavy, but it's lighter in mass compared to the cannon. So what happened in this case? The two forces are the same. Because there is some chemical reaction in here, there is actually powder that got burned, so it's going to push on the cannonball. Because it's stuck to the cannon itself, the cannonball will push back against it. And now they have a third law of Newton. So in this case, the two forces are the same. However, one of them will suffer a huge acceleration and travel a long distance, whereas the recoil motion of the cannon is probably hardly noticed. Okay? But there is one, nonetheless. The cannon will recoil back, will accelerate in the opposite direction. Because if it's a huge mass, we will see the acceleration less. We will see it move back a little, not as much as the cannonball. Same thing in the case of the bullet and the gun, for example. The bullet is a lot lighter than the gun, so it's going to travel very far with a high velocity because it gains that much velocity, and because of the acceleration, it has a higher acceleration than the gun. But the gun will recoil anyway. So the gun will actually, if you have it on your shoulder, you'll feel it, okay? That you will feel that motion backwards. So that's why you have to really have the gun firmly in your hand. Otherwise, the shot could go anywhere, okay? So this is, again, the idea that we were talking about. And in this situation, the reason why the cannon will recoil less, in a sense that the change in motion is going to be less than that of the cannonball, is because of the difference in masses. That's all. Difference in inertia. Okay, so this is another example of, again, the same situation. You have a bug hitting a truck, okay, or a bus. So which one will suffer the biggest acceleration? It's going to be the bug in this situation because it has a lot less mass. So as a matter of fact, if you have seen them, at least in your car, they smash into the window in such a way their back will basically, their insides come out, okay? Because there's tremendous acceleration change in motion for them, whereas the force is the same. So if the truck hits the bug with, I don't know how many newtons, let's have, for example, 10 newtons, the bug actually hits the truck with the same force. But the truck, in the case, or the bus, will suffer the least. The acceleration is because of this point, because of the second law of Newton. So the two forces are identical in this case. Here is the point I was making earlier about the free body diagram. What do we mean by system? That is a key thing in this case, okay? We have an orange engineer sitting in a car, and it's being pulled. So as far as we can tell, if this is your system that you're studying, then in this case, this force is an external force. So you say F equals to ma and you're done, okay? Whereas if now you include, because you're asking, for example, how much the apple is applying a force on the orange in this case, if that's the interaction, well, the two forces are equal in magnitude and opposite in direction. But my system, my free body, the system that I want to isolate is this one. So as far as concerned, this interaction is external and this force is external. So we don't, we basically have to take care to include it in the calculation. Now, if my system, on the other hand, includes both of these objects, then in this case, the interaction is an internal interaction between the two of them. So if I'm considering studying both of them and see how they move, I have to isolate them from the rest of the universe. In this case, probably the interaction with the floor. Obviously, this guy, and we're going to assume in this case that there is very, very small interaction between the wheels and the floor, in the sense that this is probably frictionless. So there is no interaction whatsoever between them, other than this vertical interaction probably that prevents this one from falling to the ground. Then in this case, this motion is not impacted by this one, by at least the floor. So if I go back into the situation here, and if it's the same problem, this force is negligible, at least in this direction, whereas in this direction it's important, otherwise this thing will fall. Then in this case, this is the only force that causes a change in motion. And this is the force that caused that motion. It's still the same system as before. Whereas in this situation now, the entire system, apple and orange, has a problem now, because if the center of mass for the entire system is moving, that's because probably it's due to an interaction between the apple and the floor in this case. There is a friction in here that is happening. If I neglect the friction between the wheels and the system in here. So there is an external force that still causes the entire system to move, and that external force is the friction with the floor. Now, if there is no friction in here, the center of mass will stay the same, and these two internal forces will not cause any change in motion because they cancel. Okay. And they do so no regardless. They cancel and they don't cause any trouble whatsoever for the entire system, even if there is friction involved. When there is a friction involved in this case, well, it's going to cause the center of mass to change, and that is an external force. It's due to the interaction with the floor, okay? So it's going to cause them, because this guy is pushing on the floor this way, the floor is pushing back on the other way. And that is a reaction of the floor that causes this motion to move forward in this case, okay? But everything else is an internal, and we really don't include it in the motion of the center of mass. So if all of the forces you have in this case are these internal forces, the action and reaction between these two objects, the center of mass is not going anywhere, okay? Now, if somebody comes in here and cuts the string between them, okay, then in this case, by virtue of the, we're going to talk about the momentum later on, okay, conservation of momentum. If one of them moves this way, the other one will move in the opposite direction. So let's not, we're going to introduce that concept shortly, okay? And case in point, the skaters, for example, on an ice skating arena, if they are standing in front of one another and one of them pushes the other one pushes back on him or her, and then they move in opposite directions. If their masses are the same, they will move with the same speed in opposite direction. It's still, in this case, what causes the motion, or at least what we think is motion, are internal forces, and internal forces should not do that. So what happened in this case, this is a case of explosion. So what happened in that explosion, the center of mass actually doesn't move. The system as a whole, the two skaters as a whole, do not move. Their center of mass, if it was in between, it stays in between. And one of them moves this way, the other one will move that way to retain the center of mass in its place. So you have to be very, very specific of what we mean by system. If this is the entire system now, what really interests us is the center of mass. If one of them goes forward, and there are no external forces now, then the other one has to move backward so that the center of mass stays in where it is, okay? So we're going to introduce that shortly in the next chapter, okay? So again, now we're just explain this point in here about the friction. So this is the friction that causes the motion forward now, because it's an external agent to the entire system now, okay? So I think that's the entire chapter and all of the main ideas for it, chapter 2. And so there is only one item in it, so hopefully you guys picked up on it, just to add it to the discussion. And then we're going to move on to chapter 3. Any questions? No? Okay, so let's move on to chapter 3. Let me find the slides for it too. And I think I introduced it already. Share screen, and that's chapter 3. You guys have all the slides and everything else. There was one of you who asked me about the textbook. So I think we will be using at some point the textbook for some of the assignments, but not as heavy as probably you might think. So instead of buying the book, if you can just rent it, that would be plenty, okay? And I know one of you guys, I don't know if it's in this class or the other one, they mentioned that they already have a PDF version of it or something like that from a publisher, which is fine too, okay? Anyway, the concept of momentum and energy are really a consequence of the laws of Newton, really, in a sense that I just introduced them earlier. So they're related, and sometimes actually when we're doing problems in physics, they help us solve a lot of the problems in physics, and they help us understand a lot of what's going on in these terms. There was an interesting discussion. I don't know if it's in your book or the other book. I think it's in your book too. But what's her name? Emily du Châtelet, who was a French lady in the 1700s. She translated the work of Mr. Newton to French. And she was actually famous also for her work in science too. And actually she gained authority in the field, and people respected her. Among other things, also she was also a philosopher, and also she published also on theology. So she was well. Let me write her name in here. I don't know if it's in your book or not. Let me write her name in here. Where is my pen? What is it? I'd like you guys to learn more about her. That's actually the Châtelet. I think the A has the accent, the French accent on it. She was actually married to Voltaire, if you guys are had any kind of philosophy or okay, until she died. Actually, he apparently after that he was very, very much basically devastated with her death. She died after giving birth at the age of 42. Anyway, the point is, there was a debate there at that time about the something that objects tend to have. Okay. And that is actually in English it was called, what is it? Oomph or something like that. That's the word that they use for it, okay? And they wanted to understand what that is. They suspected it must be proportional to the mass times velocity, okay? That's the debate. Is it really proportional to the mass times the velocity when object is in motion, really, okay? Or is it proportional to mv squared? Mass times the square of the velocity. That was a debate around that time into this something called an oomph. Later on, we called it kinetic energy. But it's really in here somewhere, okay? The work energy, it's all over the place. So the KE stands for kinetic energy, okay? And she settled the debate actually into the fact that it's proportional to the mass times velocity square. She actually did not do the actual experiment, but she refers the work of somebody else who basically what he did was he took different masses, okay, of objects at different heights and used the clay. This is not actually clay, but it's similar to clay, okay? So, and he dropped it on that clay and noted the effects of the velocity on the dent formed by the falling object, okay? And what he did was he made sure that the object will fall at different rates because we knew at that time about the laws of the work of Mr. Galileo. So he knew how to find the velocity or how to get the velocity. So this is what basically she argued based on his work, that if you double the velocity, according to the data, the dent is actually quadrupled. It did not just double, it quadrupled. It went by a factor of 4 from what it was before, okay? The depth, if you wish. How much deep it was before versus how much deep now it is because of the doubling of the velocity. Then he tripled the velocity. He made it so that when it falls, now the velocity is actually 3 times as much as it was before. So now the depth, again, went from whatever it was by a factor of 9, which is exactly what the square law would say in this case, because 3 times 3 is 9, and 2 times 2 was 4 in the second case. So she made the case for it, and that's basically how the debate was settled because of her work, okay? So again, we're going to be introducing this concept. It turns out MV actually is related to another key concept, and that is the momentum. So, and they're actually direct consequence of Newton's laws of motion, both of these quantities. So this is momentum, and this is actually with a factor of 1/2, that's all, becomes the kinetic energy, okay? And the debate was resolved at that time. Okay, so this is basically the two concepts that we're going to be talking about in this chapter. Energy is something that is as real as anything else that you can think of. However, for the most part, it expresses itself in a transit between two states through work or heat, okay? Through work or heat. Come on. Is my computer making this noise? Because I hear voices. Again. Sorry. No, what is this sound? Do you guys hear it, or am I the only one who's hearing this thing in here? Oh, wow. It's not much anyway. I thought it's one of you guys' audio that is on right now. Anyway, So let me continue with this point in here. So again, work expresses itself in terms of, or at least energy is expressed in terms of work, okay? So that is really how the key is in here. So objects, they do interact, and sometimes it does work, but we're not going to talk about heat for right now. We're going to talk about heat when we get into thermal physics. But the work is the way that is expressed in this case. So here is the idea. I have an object sitting in this position in space. I'm going to label it position 1. It has specific location in space and probably also velocity too. So it has position and velocity. If I inspect the object a little later, it's in a different place in space. It has moved, okay? And that motion now is governed by the laws of Newton. Remember, law number 1, 2, and 3. But it ended up in a different state now with a different location in space, position, and also velocity. Well, in going through this path, it must have obeyed F equals to ma and all of the laws of Newton. But then there is a change in quantity, and that change in the quantity is the kinetic energy. Because we started with the velocity, remember 1/2 of mv squared, and we ended up with a different velocity, a new 1/2 of mv squared. And the question is, how did the force do this whole thing for us? It turns out the answer to that is through this concept, the work energy theorem. The work energy theorem is very, very much equivalent to the laws of Newton. That is basically what the essence of this chapter is. The conservation of energy in here is actually more different than what you guys probably hear when you hear the politicians talk about it. When we mean in here, it's really a physical concept that is actually connected to the previous work, which is the work energy theorem. And we're going to talk about machines, and it turns out that there are some 6 simple machines that can do work, that can actually help us do work by minimizing the effort or changing the direction of the effort, okay? One case, for example, that comes to mind is the pulley. That's a simple machine. A pulley will help you change the direction of the force. Technically, if you want to lift something from the ground up, you have to go from the bottom and lift it up. Usually that's very hard. Or go beneath it and lift it up. So what you do instead of lifting and exercising this effort to lift whatever, let's say, for example, 100 pounds, which is very heavy, then you lift it up this way and you'll find yourself working very hard to do that. Or the other alternative is actually to pull. Put the thing on a pulley and wrap a rope around it and then pull in this case. So the effort in this case has changed direction. If you combine pulleys, 1, 2, 3, 4 pulleys, you might even have less effort because you take advantage of the ceiling in this case, for example, to minimize the number of the effort. And that's why you go to a mechanic shops, for example, some of the old ones that did not have mechanical, electrical lift, they use actually mechanical systems using pulleys to lift entire engines of cars from a car transmission or something like that. And the whole thing rises. So that pulleys is an example. An inclined plane will turn out to be also an example of a simple machine. A wedge also is an example of a simple machine. And gear also is an example of a simple machine. And I'm trying to think on top of my head, there are 2 others that I am forgetting. A lever also is an example of a simple machine. There are about 6 of them that are known. Any combination of these simple machines becomes a complex machine, and complex machines is what we see on a daily basis, okay? We're going to talk about the efficiency of machines in general, and then the sources of energy. The concept of power and work are related to one another. We're going to talk about this connection between power and energy. Power is what you do when you go to the store and buy, for example, a 60-watt light bulb versus a 100-watt light bulb. That is the power, actually. Okay. So let's talk about this chapter now. So this is in a nutshell introduction to the entire chapter. So the momentum has to do with mass and velocity. momentum, usually the symbol for momentum in physics is P, and the expression for it is mass times velocity. An object has to have mass to have momentum. An object has to be in motion to have momentum. And this is what we mean by momentum, okay? That is what is meant by it. So case in point in here, momentum is inertia in motion defined as a product of mass times velocity. Bigger mass will yield bigger momentum. Bigger velocity will yield bigger momentum. Case in point, a bullet, for example, has less mass, okay? You throw it, you grab it, there is no problem with it. But a bullet traveling at 300 meters per second, that is actually it has a lot of momentum. It can kill an elephant. That is actually a dangerous thing, and that is the momentum. An elephant, which has far more mass than a bullet, yet it can penetrate that because of its momentum. So the combination of mass times velocity is what we mean by momentum. And again, I explained earlier through the examples of the skater, is when you push in this case and the other one pushes back, and that situation. So let's say, for example, this is the skater one, and this is, I know they are bad drawing of skaters, okay, so don't laugh in here, okay? So this one pushes on this one, and the other one pushes back on it. That is what it meant by the third law of Newton. So in this case, this is my entire system. The center of mass is somewhere in between them. As this one starts to drift back with his or her momentum, the other one will drift in the opposite direction with his or her momentum. And if the momentum initially was 0, so there was no momentum, at the end there should not be any momentum. The sum of this vector, because actually they are vectors, remember vectors have direction, one of them is pointing the other this way and the other one is pointing that way, and these two vectors will cancel each other. So this is a case of an explosion, actually. Think of the explosion. You have a bomb, and you drop it, or it explodes. Pieces will fly every which way, but the center of mass will stay where it was before if it was at rest. If it was moving and it explodes in motion, the center of mass will keep on moving in the same direction by virtue of the first law in this case, because what causes these forces are all canceling. So in this case, the first law would require that the center of mass will keep on moving in the same direction as it was before, whereas the pieces will fly every which way. And the momentum at the end will stay what it was before. So there is a conservation of momentum in that case, okay? So again, when direction isn't important, we just say mass times speed, but usually momentum is actually a vector, okay? Again, higher, I just illustrated the example with the elephant and the bullet about how the mass affects the momentum, and also how the velocity impacts the momentum. So both of them are important in this case. So a moving object has momentum. It's also, I just defined the kinetic energy, so it must also have energy, and it has speed. Therefore, the correct answer is, it has momentum, it has energy, it has speed. So here is something about quizzes and exams. Sometimes you look at the question like this one, and you know it has momentum, so you answer A on it, okay? But if you quickly answer A, and you move on to the next question, you miss part of this question, which is actually B also is correct too, and C is correct too. But all of them are wrong, actually. A is wrong, and B is wrong, and C is wrong in this case. The correct answer of the system is concerned is D. So you get a 0 mark in this example, okay? You guys understand in here? It's a good idea to read through the entire question in here. And yes, A is correct, B is correct, and C is correct. But the system here will grade you on D being correct. So if you choose D, you're going to get full credit. If you didn't choose D, you're going to get no credit whatsoever. Please, if you see a situation like this one, let me know, because sometimes I actually give you partial credit for it, okay? So let me know to go back and make corrections on this. Does everybody understand this? Yes? Here is another item that is important in terms of the entire class, not just for this chapter. item of discussion is please read all the questions before the entire question before answering the question. You guys make a note of this. I'm glad this example is here and it's too early before our first quiz so that you guys make sure you don't miss points unnecessarily, okay? If you answered A, you're right, I agree. If you answered B, you're right, I agree. If you answered C, you're right, I agree. However, the correct answer in here in this case, to get full credit for it, is D, as a matter of fact, okay? Not A and B, not A, B, and C, is actually D. Okay, as a matter of fact, the system, if you choose one, probably will not allow you to choose the other.
So if we choose one of them, to say if we choose B, will we get half credit or just no credit at all?
The system will give you 0 credit whatsoever. Canvas will give you 0 on this question, okay, if you do a B, which is, you're right, okay, I agree with you. However, if you let me know, hey, I think I messed up, I thought that this is the correct answer, and I'm right because it's correct, and I agree with you, please let me know, okay? I think I can go back, and based on your argument, I may have to alter the grade and give you partial credit, not full credit for it, okay? And that depends on the context, honestly. Does this answer your question, Orlando?
Yes, it does.
Okay, very good. So it has to be overridden. I have to really override the grade, okay? I have to actually go myself there and change it. But again, the moral of the story in here, the item in here that I want you to really emphasize on so that you guys remember it is, please read the entire question thoroughly before answering the question, because it might be not the choice that is correct probably in your mind, okay? Okay, again, when the speed of an object is doubled, its momentum will double in this case. That's easy because it's mv. So if you go from 2 meters per second to 4 meters per second, the momentum, okay, let's plug in numbers in here. It's a good idea to have numbers. I mean, physics is science of that relies heavily on math. Let's say, for example, for the sake of argument, you are in a car that weighs 700 or 900 kilograms, okay? And the car is going at, let's say, for example, 20 meters per second. That's not a lot of velocity, by the way. 20 is about 30 miles per hour or something, okay? So 36 miles per hour to be closer to the correct answer. So how much momentum are we talking about in here? So it's really 20 times 900, so 2 times 9 is 18,000. The units for the momentum is kilogram meter per second. Velocity times mass, okay? So that's how much momentum you have. Let's say, for example, you double the speed. Now, all of a sudden, you're not cruising at 20 meters per second, or you're doing 70 miles or 80 miles per hour. So you're doing 40 meters per second, okay, in that car. So the new momentum now is going to be this number, 900, times 2, because times 40 instead of times 20 now. And the answer obviously is going to be 36,000 kilograms meter per second. So that answers it now. If you double the speed, you double the momentum. Does this make sense now? Yes?
Yes.
It's usually numbers help you say a lot of things without saying a lot of things, really, okay? That's why equations are used heavily in physics, because sometimes those equations, they can be, you can write basically several pages on them just to describe what they're talking about. But numbers tell you a lot of things just by virtue of putting them in front of you, okay? The impulse is really the change in momentum, and it's force times the time it takes for it, okay? If you have a short gun, for example, short barrel gun, I should say, versus a long barrel gun in this case, which one will result in higher momentum when the bullet comes out of? In this case, the powder has a lot of time to push the bullet with the same force. Let's say, for example, you have 10 newtons. And in this case, let's say, for example, it took 4 seconds to accelerate it, whereas this one is 10 newtons, but let's say, for example, 1 second. So the change in momentum in here, or the impulse, is going to be 10 times 4, which is 40 Newton second, or the same thing, 40 kilogram meter per second. Impulse and momentum have the same units, okay? In this case, it's only 10 kilogram meter per second. So if you have a bullet, for example, in here that weighs, let's say, for example, I'm going to put a big bullet in there, okay? I'm going to put a 1/10 of a gram, okay? That's actually a 1/10 of a kilogram. So that's going to be 100 grams, 1/10 of a kilogram. So that is how much times the velocity of the bullet is equal to, in first case, 40. So that means the velocity is going to come out with is 400 meters per second. So it's going to be supersonic. It's going to travel faster than the speed of sound, which is 343 meters per second. So the first gun. The second gun instead is going to go 0.1. That's the bullet. It still weighs 100 grams, by the way. Times the velocity is equal to 10. It's going to be way subsonic. It's going to be 10 over 0.1, which is about 100 meters per second. I'm just doing the math. You're not required to really understand a lot of how this algebra is coming about. But the point being in here is, if you give it more time, the force, it's going to result in a higher velocity than if you give it a short time. That's intuitive enough. If this guy, for example, is taking a long time pushing with the same force, so if he can do 10 newtons and have the 10 newton for a long, long time, this person, the acceleration in this case will be constant, and the velocity at the end when he let go of it is going to be higher, obviously. But if he just pushes it a little and give it just a small kick and then let go of it, it did not have much time to gain a lot of velocity. So that's intuitive enough. And the example I gave in here for a long barrel gun versus a short barrel gun, then in this case, the gun will have a lot of time for it to gain that much speed. Obviously, in this case, I forgot to include the friction. I neglected the friction, I should say. And the effects, this 10 Newton will be slightly less than 10 Newton, and the effective acceleration, or the effective velocity will be less than the 400 meters per second, which is actually supersonic speed, higher than the speed of sound. Whereas in the second case, it's going to have also friction, but less friction. So it's got the 10 Newton will be less. So the force is the same, but the time matters. Okay, so that's what the concept of impulse is. When the force that produces the impulse acts for twice as much time, the impulse is doubled again in this case. So that's intuitive enough, okay? Again, force times, this is what I was talking about. This delta means change. So whenever you see in this class the symbol delta, it means this same thing. It means the word change, okay? So the impulse is what do you mean text? I don't understand text. You mean test?
Like the questions that like you have, like the moving object has a momentum, speed, energy, and all that. Like, are those going to be on the?
We have conceptual questions. Yes, I really need to understand these things, Andrea and Orlando. Okay. So the impulse is the change in momentum. This question is important, so you might be tested on it, okay? So this stuff is key to understanding these things, okay? So the impulse is change in momentum. It's not momentum, it's the change in momentum, okay? That's a key thing in here. It's the difference actually in momentum, not the change. Actually, the change in here in this case is kind of a, usually the word change is reserved for rate. This is not a rate, not a rate. But just the difference, the change is the difference, okay? We went from this value to that value. That is the impulse. And that's why I used before deliberately in purpose the same units, because they are. Newton times second is actually the same thing as a kilogram meter per second, because a Newton is a kilogram per meter per second squared, and cancel the second squared with the second that is upstairs, and it will end up to be the same thing. So they actually have the same units, but they are not exactly the same concept, because one of them is the difference of two quantities. The impulse is the difference between two momenta, momentum before and momentum after, momentum 1 and momentum 2. That is the impulse, okay? So you either apply a great force or you allow the same force to be applied for a long time. That is basically what how you increase the momentum, okay? Different way of doing the same problem before. For example, if I really want to have a supersonic bullet, and it cannot make the barrel longer, then in this case, I have to increase the powder inside, provided that my gun does not explode in my hand, that's all, okay? And then instead of applying 10 newtons, I could put 14 newtons there for 1 second. 40 times 1 second is going to end up with 14 newton per second, or 40 newton second, or 40 kilogram meter per second squared. So if I put far more powder in the gun, or whatever causes it, or the spring, if it's a spring basically triggered the thing, whatever I need to make this force 4 times as much, if it cannot make the barrel longer, then that's the trick behind it to doing this. So either one of the two, either increase the force or give it more time to do what it needs to do. So that's the bottom line of this discussion here as far as the momentum is concerned. Honestly, on a daily experience, at least in non physics majors, you really don't deal a lot with this concept, especially the impulse. I mean, you probably deal with the momentum, but not as much with the impulse, okay? What you need to deal with from this chapter, and it's critical, and that answers you, hopefully, Erlinda and also Andrea more, is the energy. Understanding the energy is key from this chapter, more so than the impulse. Does this help a little bit, Erlinda and Andrea, and everybody who was wondering what in the world we're going to deal with this impulse? What are we going to do with it?
Yeah, thank you.
Okay, so the key of energy is actually far more meaningful from this chapter, and far more, it has applications everywhere, okay? So cases of a momentum change, so again, that's an example of how to make the momentum change over a long period of time, or versus a sudden, for example, collision with a wall. One of them will give you more time to change the momentum from a high value to a low value, meaning that the force in this case will be less required to do the same thing. Whereas if you hit the wall with T that is less, and you would want to come, let's say, for example, you were doing 40 kilograms meter per second, and you would want to bring this one down to 0, okay? You have two options. Either you smash yourself or your car, hopefully you don't do this experiment a lot, to a wall, okay? And this bring it in, let's say, for example, 0.1 second, okay? 0 second. In a 1/10 of a second, bang, you go from 40 kilograms meter per second down to 0. Then in this case, man, you're subject to a force that is 40 over this much time, which is 400 newtons, okay? 400 newtons is not bad, really, honestly. It's about 80 pounds, okay? Somebody hit you with an 80 pounds, okay? That's what that means. I mean, it can leave bruises and things like that, so, but it's not as bad as more force. But imagine yourself running into a hay stack in here and bring yourself, give you more time before you slow down from this 40 down to 0. So in this case, let's have, for example, for the sake of argument, took you 5 seconds to come to a rest, to stop. You lose all of your momentum. You lose all of your impulse in this case. The impulse is exactly negative 40 kilograms, because it's usually the final minus initial. So in this case, you say 40 divided by 5 is 8 newtons. 8 newtons is slightly over a pound, okay? That's not bad. Which one would you rather be hit with? About an apple or an 80-pound thing? So that's the example in here. So the impulse has to do with the time, okay? That's the example I was giving in here earlier. So there is very little damage to the truck in this case because the force in this case is less, because it takes a long time to come to a rest. The brakes fail on it and it needs to come to a stop, okay? So what you do in this case, you put hay in front of it and the hay will slow it down enough to come to a rest, but it's over a long period of time. Or put wall in this case and bang, in this case, it's gonna come stop right away, but the force will be great, so the truck will be far more damaged. Same thing with these examples in here, okay? So again, this is actually the momentum in this case over a long period of time and also over a short period of time, okay? So when you hit it right away, you produce a lot of actually force in that case, okay? So that's why this athlete, actually she's using the process backward now to make more damage to this bricks in here. But imagine her trying to come very gently, trying to break the bricks in here, okay? Not gently, I should say very slow, okay? You put the brakes in here, there and there, and then comes in here and try to break this one in here. Doesn't work, does it? But if she comes in very quick, she will produce more damage to them than if she goes very slow. You guys understand what the impulse now has to do with what? And how it's related to the time and the force? Again, I talked about the conservation of momentum. In every case, the momentum of the system cannot change unless it is acted on by external forces. And the illustration I was talking about earlier in the case of the explosion, those are internal forces that cause the explosion, whether chemical or the two people pushing against one another. They are not going to count. What needs to count in here, if you expect the momentum to change a lot of the system, is it needs to be external forces. In the case of the explosion, the only forces involved are internal. Therefore, the entire momentum did not change. So if the bomb was sitting in a place and then it exploded, then the thing with it is the momentum was zero before for the entire system, and it stays zero. Its center of mass does not go anywhere, although the pieces will fly every different direction. In the case of the two skaters, when one of them pushes on the other one pushes back on her or him, then in this situation, there are internal forces. The center of mass stays in its place because the momentum was zero to begin with, okay? So that is the conservation of momentum. A system will have the same momentum both before and after. Any interaction occurs when the momentum does not change. We say it is conserved. So when you hear the word conserved in here, that means the before is the same as the after. Before what and after what, it's just a matter of choosing your events, that's all. Sometimes the before can be after and the after can be before. That's really depending on how you're looking at the movie. Are you playing the movie forward? Are you playing the movie backward? So that's really how this thing is. So the momentum before, that's what we're talking about, and the momentum after are the same. So in this case, we say it's conserved. Okay. So any quantity that suffers no change before and after is called conserved. And that's what we mean by actually the conservation of energy in this case too. It's coming down the road in here. So that's exactly what I was writing in there. Mathematically, this is what that means. The total momentum before is the same as the total momentum after. And this is also in the case of collisions too, okay? So the net momentum before collision is equal to the net momentum after collision. That's basically what the conservation of momentum in this case is. Why is this thing is? Yeah. Okay. So that is the opposite of actually. So this is actually an implosion, not an explosion. What we mean by it. That's what we typically associate collisions with. Collisions are actually more generic. They can be the case of a collision, or they can be the case of an explosion. Both of them are the same thing. So they are going to be collision as an implosion or as an explosion. Both of them are the same thing as where momentum is conserved. There are two kinds of collisions though, whether implosion or explosion, and they are called the so-called elastic and inelastic collisions. In the case of elastic collision, the kinetic energy is conserved. Whereas in the case of the kinetic energy, in the case of an inelastic collision, is not conserved. That's all. That's the difference between them. Actually, there is two different kinds of, there is a third case in between them. Here are the extreme cases. The kinetic energy, usually we use the symbol KE for it, okay? So the kinetic energy before and the kinetic energy after, so I'm gonna say the change in the kinetic energy is equal to 0. That's usually this case, no matter what. One, there is a full, basically fusion of the two objects in the case of the collision. You have a car 1 and a car 2, and they come in and they fuse, they become one car. So in this case, I say this is an inelastic collision. Or two objects, they were held together, let's say, for example, with a Velcro, and now all of a sudden they come apart. Okay, that is actually a case of also collision, albeit it's an explosion, but also that is an elastic, a perfect inelastic collision. Okay. Most collisions, though, are somewhere in between. They are not exactly 100% elastic. They are not exactly 100% inelastic. Okay, so that is the case with it. So let me give you an example. So this is the example of elastic collisions. This is the entire room where you are right now. It doesn't matter, just look around. You will see particles that are flying every which way. Those are the hydrogen, not hydrogen, oxygen and nitrogen molecules. Do you guys see them? Can you look around in your room and see? Yes? They are everywhere. The entire room is full of them. It's actually those particles in here. Okay, they're colliding and going around. That's actually what you feel as temperature. Okay, oxygen colliding with oxygen, or colliding with nitrogen, and nitrogen is colliding with nitrogen, or colliding with oxygen. For the main part, there are other elements in the air, but that's basically what causes these things. And that collision is an elastic collision, and it's bouncing off of the walls, and it's bouncing off of you, and that's what you feel as temperature, actually. Okay, all of this is an example of elastic collisions. Okay, so that's an example of an elastic collision. So again, they're all colliding, and they're colliding with walls and moving things around. Conservation, this is a case of an inelastic collision. Here is a problem. When they fuse in this case, okay, those are two train cars. Once they fuse, one of them is coming with 10 meters per second. And let's say, for example, both of them have the same mass. So once they fuse, the momentum before, how much moment, let's say, for example, this one weighs, it doesn't matter how much weight it has, okay? Just for the sake of argument, say this one is 1,000. Usually it's much more than that for train cars, okay? And this one also is 1,000 kilograms. So I wonder, how much momentum did I start with? I have 0 times 1,000 plus 10 times 1,000. How much is that? Do you guys agree that it's 10,000 kilogram meter per second plus 0? Yes? Now, once they fuse, this was 1,000 and this was 1,000 kilogram. How much kilograms do I have once they fuse now? How much? How many kilograms they fuse now combined? Thousand and 1,000. How many kilograms they are now? Okay, thank you, Daisy. So it's 2,000 kilograms. And I need to know to multiply this number by some number to make it equal to the same 10,000 that I started with. Remember, I had 10,000 kilogram meter per second to start with before the collision. And now I need to multiply 2,000 by a number to get it exactly to 10,000. What number should I multiply 2,000 by to get 10,000? 5. Thank you very much. So it has to be moving now with 5 meters per second. So as they fuse now, it's moving slower. Do you guys understand that? Because initially, the first one was moving super fast, 10 meters per second. Now, when it fuses with the other one, the new momentum needs to be the same as the old momentum. Because case in point in here, 5 times 2,000, that's still 10,000 kilogram meter per second. In other words, it's moving slower. Okay, so this is a case of an explosion, an implosion in this case. Okay, the two objects fuse and now they are moving. So the momentum helped me determine how fast the two objects are. Let me give you another example in here of a collision. Let's say, for example, a car that weighs 1,000 kilograms moving at 20 meters per second, and another car that weighs also the same mass, okay, 1,000 kilogram, and moving 20 meters per second, except this one is going this way and this one is going that way. How much momentum is this one? I have 1,000 times 20. Isn't this 20,000 kilogram meter per second, correct? And this one also is 20,000 kilogram per second, meter per second. What's the sum of these two numbers? Don't tell me it's 40,000. 20,000 plus 20,000, but the direction is opposite. So how much is the sum of these two numbers really, when I take the direction into account? They are in opposite directions. One of them is moving this way and the other one is moving this way, and each and every one of them is bringing 20,000 momentum with it. And they are in opposite directions. And it's not 40,000, it's not the sum of the two, plain and simple. So what's 20,000 plus the opposite of 20,000? I need the number. Very good, Genesis. Yeah, that's 0. They cancel. So I had no momentum to begin with, because both of them are in opposite directions. They're coming into one another, so I had no momentum. So when they collide and they fuse, they don't go anywhere. They stick to one another. So I lost all of the momentum also. So this is the same thing, except the first case, they were actually, one of them was stationary, the other one was moving, and the other case were both of them moving, which I'm wondering about what happened to its energy. Obviously, the energy is gone. And we're going to talk about that one actually next time around. How far are we in this? Oh man, we did not even finish the momentum yet. Okay, since the concept of work is an important concept, we're going to stop at slide 34. Let's check this example quickly. Freight car A is moving toward identical freight car B that is at rest when they collide. Both freight cars coupled together, compared with the initial speed of the freight car A, the speed of the coupled freight is. I just basically looked at it. We just did the number in here. So initially, both cars are the same. One of them was moving at 10 meters per second. The other one was not moving at all. And then once they fuse, how fast it's going to be moving? Is it going to be moving with the same 10 meters per second as a combination once they fuse? Or is it half of what it was before? So the correct answer is half. Yes, thank you very much, Tanner. That's correct. We just did the algebra for it because they have the same mass. One of them was not moving, the other one was moving. So how much momentum we had? It's all of it in the car that was moving. Once they fuse, that momentum that was in the car that was moving split itself equally between the two cars, because now they need to move with together in the same direction. Because now we have twice the mass, the velocity needs to be by half. If I double the mass, the velocity needs to go by a factor of 2, because all of a sudden after the collision, now I have twice as much mass to make up the same momentum I started with. So the speed better go by a factor of 1/2, so that the 2 will cancel and I keep the momentum the same. Okay. Any questions? I know that we're stopping at slide 34, which is barely halfway. Next time around when we come in, we're gonna talk about work and energy and everything else.
I have a question.
Yes.
So you just want us to post in the chapter 2 part 2 discussion and not the chapter 3 one yet?
Yeah, let's keep the chapter 3. There is already an item that I'm going to remind you guys of it next time around when we meet, which is this Thursday. Okay. And also we should be ready for the quiz for this Thursday too. Okay. So
Okay.
yeah, that's a good question actually, because I was hoping to advance more, actually get to the energy and things that are a lot of fun. But even momentum is not that really. Okay, it's a lot of fun because one question is, hey, a car was going 50 miles per hour, and another car was going 50 miles per hour, and now they collide. So the first car must have had a lot of kinetic energy to go with it. That's motion energy in motion. And another car that was actually moving too, so it has also a lot of kinetic energy. So where in the world did the energy go when they collide? Because both of them stopped now. That's going to be actually item 2 of the discussion from this chapter. I want you guys to think about ways that the energy has gone because it was there and now it's not there anymore. Okay. But that's going to be, let's leave that until Thursday. Thank you very much, guys. Any question other than this?
And the test that we have, the quiz, it's just chapter 1 and 2, or is it chapters 1, 2, and 3?
It should be only 1 and 2. I will adjust it accordingly. Okay.
Okay, thank you.
Okay. Thank you. Okay, guys. I'll see you Thursday. Be safe. Okay. And don't forget you have an assignment that is due today. Okay. For the first assignment for the discussion that you guys are required to do it today. So please make sure that you guys finish that.
Thank you, Professor.
Thank you, guys. See you on Thursday. We stop the recording.